This is section 3.9, related rates. When blowing up a balloon, both the volume and the radius of the balloon are increasing, and the rates of increase are related to each other. It's much easier to measure the rate of increase of the volume than it is to measure the rate of increase of the radius. In this section, we introduce the idea of related rate problems, which involves computing the rate of change of one quantity in terms of the rate and change of another quantity, which may be more easily measured. So first of all, this section's big. You can expect to see a problem on your exam, and you can expect to see a problem on your final that's coming from 3.9 related rates. The first example on here says air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So first thing is that we have a balloon. It is a spherical balloon. And so we have to know a few things about this. We have the volume is increasing at a rate of 100 centimeters cubed per second. It wants to know how fast the radius is increasing when the diameter is 50 centimeters. So first thing is that we are dealing with a spherical balloon, and we're talking about volume and we're talking about the radius. So I need to have a formula for this in order to relate those two things. So we know that the volume of a spherical balloon is going to be 4/3 pi r cubed. And we also know that the rate of the volume increasing is at 100 centimeters cubed per second. And what that is since it's a rate, we're talking about a derivative, and it's with respect to time. So we know that dv dt is equal to 100 centimeters cubed per second. So what we're asked to find is how fast the radius of the balloon is increasing. And so how fast, again, that's another word for a rate. So we're going to we need to find dr dt. So we need to find dr dt when r is equal to, well, if the diameter all the way across the balloon is 50 centimeters, the radius is going to be 25. It's half of that centimeters. So in order to do this problem, if you notice, I have an equation up here that relates the radius and the volume to one another. And I also have rates here, which means that we're going to have to be taking a derivative. So I need to take this derivative with respect to time on both the left and the right side. So this is using that implicit differentiation that we learned earlier. And so the derivative of v with respect to time is going to be dv dt. And then we have 4/3 pi r cubed, and we have to take a derivative of the right side with respect to time. Well, 4/3 and pi are just constant. And so if you notice, we have the power rule. And so 4/3 pi times 3 is just going to be 4 pi r squared. And again, we're taking the derivative with r with respect to time, so dr dt. So if you notice, now we have dv dt and dr dt. And I know that dv dt is 100. And we are asked to find dr dt. So I'm going to go ahead and substitute in what we do know and what we are trying to find. I'll leave as a variable. So we know that dv dt is 100. I'm going to leave off my units for now. I know 4 pi r is 25 squared. And then we have dr dt. So going ahead and solving this, I'm going to get dr dt is equal to 100 over, if I divide both sides by 4 pi times 25 squared, which is going to simplify to, if you think about 4 times 1 of the 25s would equal 100. That would simplify to 1 over 25 pi. And this has to have units with it, which is one of the big parts here. So we know that it's dr dt. So we measure our radius in centimeters, and our time is measured in this problem in seconds. Also, the answers here are always left exact.